finally get started. So we've finished our configuration steps over here. We've got everything here. We can close this .env file. And we can open up our Solidity file. And now we're starting the next step within this tutorial. So yeah, let's begin. So firstly, let's start off with some very basic stuff, comments. So double slash means it's a comment and everything on the rest of the line is a comment. If you want a multi-line comment or, a delimited comment, I should say more accurately, if it's /*, then the rest of it's a comment until it encounters the next //. Anything in between it, it's considered to be a comment. So that can span multiple lines if you want to. All right. Now, then the first line on a Solidity file is almost always going to be this thing, license identifier. This essentially specifies a short name or identifier for each license type. So in this case, mine's MIT, and that corresponds to whatever this list defines as being MIT. It is not a compiler error if you include it, but it is a compiler. So, best practice just to put it inside. All right. The next thing is to specify the Solidity version number, and we do that using a pragma. So what I'll do here is I'll type Solidity. So we're saying, okay, we want a specific Solidity number, and I'm going to use 0.817. And what this essentially does is it says only the Solidity compiler with this specific version is allowed to compile the smart contract. Now, the specification does allow for different sorts of ways of specifying. For example, you can use anything that is within semantic versioning or semver package in NPM. So, for example, you can say 0.8 point anything, or you can specify ranges, etc. But in this case, we're just going to stick to one specific version and leave it as that. Now, by way of orientation, I'll point this out again with how the tutorials work. So let's scroll down to the step that we're at the moment for you following along. So in the tutorial, you'll see heading titles. Some of them look like this: step followed by an identifier, a colon, and then some text. And that is meant to correspond to this. So you'll find a to-do, and then you'll find the text that matches this text over here. And then subsequently, you'll say step identify in the accompanying tutorial, and then that number will match this one over here. So that's just by way of orientation. In case you're following along, this is how I'd like it, how the tutorial has been designed to make it easy for you to follow along when you're reading through it. All right, so let's move on, right? So we specified the Solidity version number. The next thing we want to do is specify the name of the smart contract. Now, the way we do that is we use a keyword called contract. And then after that, we specify the name of the smart contract. In this case, I'm going to call it Troubadour. Right. And that's it, right? So anything between this squiggly bracket and its corresponding closing squiggly bracket, that's all considered part of this specific smart contract. So any state that's within it, any variables that are within it, etc., these are all considered to be part of the smart contract. Kind of similar, right? But not exactly, like a class within the object-oriented paradigm, right? It helps to think of it that way. Now, let's start with some state, right? So we'll create a primitive state variable, and a good way to start with that is a number. So this type, uint256, that's the type. And then we'll come back to these later, and then we'll have a name for it. So that's called min fee, a minimum fee. And then we assign a value immediately of 100. Because it's a primitive value, we can assign the value just like that. Now, coming back to this, public and constant, they are modifiers, if you will, on this particular state variable. What public basically says is that the value of this particular state variable is accessible outside of the contract. So anyone can query its value and find out what its value is. the smart contract actually intentionally exposes its value. Now, the next thing is constant. This means that this value is not really a state variable, but rather it is state and it just doesn't change. It's constant. Moving on, let's move on to a dynamic state variable. So a very common one that you'll see in a lot of Solidity smart contracts is something called a mapping. It's kind of analogous to a hash map, right? So let's create a mapping called amounts. So what we want to do is store a specific value or a numeric value per address, which is essentially per account that we want to track. So we're tracking a number per account. Now, in a mapping, you have a key value pair. So the key in this case is address. We want to be able to see which address corresponds to which amount. The delimiter between the key and the value types is the symbol equals an arrow, and then 256. Right. And that's it really. So this effectively means that if you look up a particular address, then you can get a value that happens to be a number, an unsigned integer. And the name of that is called amounts. We will make use of this later on in our implementation of the functions. All right. So now the next thing is we will talk about some functions. So let's take a look at this function over here, total burn. So just by way of orientation, keyword for function, name of the function, parentheses to denote a parameter list, and then you've got squiggly brackets, open and close, and in between you have the implementation. So based on that, it's pretty similar to the function syntax that you may be familiar with when working with JavaScript. So we're not going to say highlight that kind of syntax again. Instead, we'll focus on what the differences are between Solidity and JavaScript in terms of function syntax. And the first thing that I'd like to cover is function modifiers. So we saw public earlier on, and that means something that is visible from the outside or accessible from the outside. And that applies, to state variables as well. And functions can also be public. In fact, many of them are. So let's specify public for this one. We want this burn function to be public. And we also want it to be something called payable. This is EVM specific, saying when we call a smart contract with a transaction, you can send any amount of value with it. And that value will be denominated in the native currency of the network, which happens to be HBAR in the case of Hedera. So if you if this smart contract is deployed to Hedera testnet, then if you have testnet HBAR, you can send it along with the transaction. And what will happen is that this function, since it belongs to this Trogdor smart contract, that amount of HBAR that you send in with it gets added to the balance of the Trogdor smart contract. So Trogdor's balance will go up. The smart contract has an address, and therefore you can send it value just like anything else. Now, the difference is that if you want to call a function and send it a payable amount, what happens is that function has to opt in to it, meaning saying, oh, okay, I accept a payment via this payable modifier. If it doesn't have it, then the smart contract will reject the transaction. And if the transaction fails, then the value never gets added to this particular smart contract. That's how it works. Yeah, that's definitely something that's very Solidity or EVM specific. All right, and let's also do the same thing for total burn. So this one is different. This particular function does, as you can see from the comments over here, does a bunch of things that do update the state of the smart contract or the network. So that's fine. But this function is intended to be called as a form of a query. It just returns a value. So because of that, what we want to do is we actually want to specify that it is that it doesn't update the state of the network. And the way to specify that is by saying it's a view. So the view modifier says, okay, I'm declaring as the function, I declare that I will not update the state of the network. And if you include any commands inside of the function body that potentially modify the state of the network or of the smart contract, the compiler will just reject and refuse to compile. So there's a compile time check for that. All right, so view. The other thing that we'll do is something called external. So this is essentially the same as public when it comes to a function. Almost the same as public. The key difference is that a public function can be called by the smart contract itself and by other smart contracts or accounts, but an external function cannot be called within the smart contract itself. It can only be called by another account or another smart contract. So that's essentially what it does. So there are a few different modifiers for you to explore. There's private, protected, external, and public. So there's quite a few of them, 4 of them to be specific. All right, sorry, public, private, internal, and external. Those are the 4 ones. Now, moving on, let's specify a return value. Now, this function over here, burn-init, modifies state and doesn't have a return value, doesn't need one. This one over here specifically does need a return value. So we want to return a balance, and any balance on any account of smart contract is always of type UN256 because that's how it's defined in the network. So this is the syntax. So we say returns, and then in parentheses, a list of types for whatever's being returned. So in this case, we're only returning 1 value. So that's great. Note that unlike JavaScript and possibly several other languages, Solidity does not restrict you to only returning a single item. You can return multiple values from a single function. That's allowed. All right. Now, let's move on to special values that are accessible within a function. So when you're in a function, typically you can, like, let's say you're doing something in JavaScript, you can access anything that's inside the parameter list of the function. And you can also, if that function is within a class, it can access the member variables of that particular class. So in this case, you'd be able to access min, fee, and amount as well. However, in smart contracts, functions also have access to like some sort of network state kind of things. And so these comes from things like the block, the transaction, and several other things. So 2 of the important ones are called message.sender and message.value. So message.sender essentially is a way for a smart contract function to know which address was responsible or which account was responsible for invoking that particular smart contract function at that particular time. And the message.value is applicable in the case of payable, where it knows how much HBAR, in this case, was sent into the smart contract. All right, so with that introduction out of the way, we're ready to do the first condition. So require is a built-in function within Solidity language specification itself that essentially throws an error and therefore cancels, reverts the transaction from that function invocation unless a specific condition is met. So in this case, we're going to set a condition that message.sender is not equal to address 0. Now, this is a common check in a require statement, checking that it's not possible to use a null address because this address is a sort of a special case. We don't specifically need it in this thing. We just wanted to sort of demonstrate how to do that. So let's interpret what happens. So if this function gets called, if this condition is satisfied, the function execution is allowed to go to the next step and the next step. But if this function condition is not met, so this evaluates to false, what happens is this message is this text here, the 0 address not allowed, is the error message, and then it reverts the entire transaction. So any state changes that may have happened up until this point in time as part of the execution, they just get thrown out the window, and it's as if this transaction never happened. So that's essentially what a require statement does. So now we're going to do the same thing with another condition, message.value. So this is essentially the amount of HBAR that's sent in, needs to be more than or equal to the minimum fee, which is a constant value of 100. So the smallest unit in Hedera networks is a tiny bar, which is like 10 to the power of, I believe, -8. Essentially, yeah, 10 to the power -8 of a full HBAR. So you need that to at least 100 tiny bars in order for this to succeed. This requires statement to allow the function execution to proceed. So let's use that and say pay at least minimum fee. Now, I'll make a sort of comment here that this is a common pattern in smart contract functions, where they start off with a set of required statements to ensure that the function is being invoked in only a valid way before the actual main thing that the function does is allowed to do. So this pattern of require statements followed by execution statements, which we'll get to shortly, is a pretty common pattern, right? All right, so let's do the actual useful stuff. So let's update some state. So here we want to keep track of how much payable amount any specific address has sent into this smart contract. So we'll do amounts message.sender plus message.value. So we're actually making use of this variable. So message.sender is incremented by message.value, and then it's stored back inside of this mapping. So that's essentially what this does. So each time this function is called and these two require statements do succeed, then we expect the message.sender address, whatever its value is, to be incremented by message.value amount. Now, the next thing we want to do, this is again another pretty common pattern, is to emit an event when there is a state change that is of interest. So in this case, we want to emit an event. But before we can emit an event, we have to specify that event. So let's scroll up here to step 18, and we can find the burnination event over here that's been named. So we just need to include the keyword of the event. And then inside of it, we specify the event parameters, or I should say data. So these are the fields that the event contains. So basically, who as an address and amount as an unsigned integer. That's what we want to emit. So now that we specified the event, we want to emit it. So this time we have the same name, burnination, and burnination over here. So let's emit that burnination event. And now we need to fill in the values of who and amount. And I think it might be almost intuitive by now that the who is going to be an address, which is message.sender. And the amount is going to be a unit 256, which is message.value. Quite straightforward, this one. All right. So that's it, really. I believe I've covered the entire syntax of the Solidity part of that we've used, at least within the smart contract. Now, this smart contract is extremely simple. There's a ton of different items in terms of syntax that we have yet to cover. But, this is good enough for the purposes of the tutorial. So yeah, let's move on. So now, just to wrap up this sort of introduction section of the tutorial, let's talk a little bit about software libraries and developer tools. So in order to interact or develop with smart contracts on Hedera Smart Contract Service, which is essentially the EVM offering from Hedera. You can do so in multiple ways. Now, this tutorial will cover two different ways of doing it, or two different approaches, I should say. One is to do it like the Hedera native way, and you can interact with the Hedera Smart Contract Service using Hedera SDK.js, and that has its own API. The other option for you to use is to use something that would be familiar to you if you have experience in working on smart contracts on other EVM compatible networks, for example, Ethereum itself or any of the other networks. So for this, you'll need a JavaScript library that is designed to talk to JSON RPC APIs and also has other functions, for example, like the one you saw earlier on, where you take a seed phrase, a bit39 seed phrase, and turn that into a set of accounts, all that sort of thing. You need a software library to do that. The popular ones are Ethers.js and Web3.js. And in this workshop, we will be using, among those two, we will be using Ethers.js. Now, the next thing is Solidity, a Solidity compiler. If you use something like Hardhat, that tool will manage Solidity for you, and you will see that in action later on in this tutorial. Alternatively, you can also use the Solidity compiler directly. There are multiple tools that have that available. In this tutorial, we'll be using the Solidity compiler directly, and we'll also use Hardhat's managed version or equivalent of the Solidity compiler as well. Now, I'll point out that in order to write EVM compatible smart contracts, Solidity is not the only option. There's also another option, several other options, in fact, the most popular, which is Viper, but we're not going to cover that today. This tutorial is going to be all about Solidity. And finally, in order to work with smart contract development, there are several sort of development frameworks. We've got the popular ones are Truffle, Hardhat, and Foundry. And these provide utilities, script structure, documentation, etc., that are very useful in development. And yeah, in this one, we obviously are not going to cover all of them, but we will just work with Hardhat and keep it simple that way. But essentially, this tutorial is structured in such that we cover like two different development pathways to work with smart contracts. One is the Hedera native way, where we use the Hedera SDK in order to work with it. And then the other pathway is to use Hardhat, which is more of the EVM tooling that you might be used to working with from, say, other networks. So with that out of the way, that's the end of the introduction.